Welcome to Powered by Tesla.
Have you ever just stopped and thought about that invisible force that powers, well, pretty much everything you do? I mean, from the second your alarm goes off to making coffee to the phone that's probably in your hand right now, it's all electricity.
It's so woven into our lives, we don't even see it anymore. It lights up our world. It runs our cities. It connects all of us. I mean, think about it. Our entire modern world would just stop without it. So we all get how to use it, right? You flip a switch, but what's actually going on inside that wire? What are these basic forces at play? Okay, let's get into it and break down the 3 ideas that make it all work. To really get this, we've got to think small, like impossibly small. We need to introduce the star of our show, the absolute hero of this entire story, the electron. Yup, everything, and I really mean everything about the electricity we use, comes down to this one ridiculously tiny particle. It has a negative charge, and when we get these little guys moving in an organized way, well, that's where the magic happens. And when I say tiny, it is really, really hard to wrap your brain around just how small we're talking, and the sheer numbers involved in even the tiniest spark. Okay, check this out. The standard unit we use to measure electric charge is called a coulomb. And just one single coulomb is the charge of, get this, 625 followed by 16 zeros of our tiny electron heroes. It is an absolutely mind-boggling number. So we have these just astronomical numbers of electrons hanging around, especially in materials like copper wire. But, just having them there doesn't do us any good. We have to get them moving, all together, in the same direction. And that brings us to our first big concept, current. So electric current is really just that, a directed flow of electrons. And when we measure it in amps or amps, all we're really doing is counting how many of those giant groups of electrons, how many coulombs, are zipping past a single point in a wire every single second. Of course, this flow doesn't happen just anywhere. Materials like copper, which have tons of free electrons just ready and waiting to move, we call those conductors. They're like a superhighway for electricity. But then you've got materials like rubber, which hold on to their electrons really tightly. Those are insulators. They're basically a roadblock, stopping the current cold. Now, here's something that trips a lot of people up, so it's worth pointing out. Since electrons are negatively charged, they're actually attracted to the positive terminal of a battery. So in real life, they flow from negative to positive. But, and this is a big but, because of a historical convention from way before we even knew about electrons, engineers still talk about conventional current flowing from positive to negative. It's just a quirk of history, but the actual electrons are going the other way. All right, so we've got this massive flow of particles. What's your gut tell you? How fast is an individual electron moving down that copper wire? Are we talking like speed of light? Or maybe the speed of sound? The answer is kind of shocking. The average speed of one of those electrons, what scientists call the drift velocity, is incredibly slow. We're talking less than a millimeter per second. It is literally slower than a snail. So that leads to a pretty obvious question, right? If the electrons themselves are crawling along, how come the lamp across the room turns on the instant I flip the switch? And here's the brilliant solution to that puzzle. It's not one electron making the entire journey. See, the wire is already jam-packed with electrons. Think of it like a tube completely filled with marbles. When you push a new marble in one end, another one pops out the other end, instantly. The push, the electric field, is what travels at nearly the speed of light, telling all the electrons down the line to start moving pretty much at once. So what is that push? What's the force that creates that electric field and gets all those billions of electrons moving in the first place? Well, that brings us to our next big idea, voltage. By far the easiest way to think about voltage is just as electrical pressure. That's it. Just like water pressure in a hose pushes the water out, voltage is the pressure that pushes the electrons through the wire. So a higher voltage means a stronger push, which if nothing else changes, means more current. But that push doesn't get a completely free ride. Just like water flowing through a hose runs into friction, those electrons are bumping into things and getting in each other's way. And this opposition is our third and final core concept, resistance. Resistance is, well, it's exactly what it sounds like. It's a material's ability to resist the flow of current. You can think of it like electrical friction. And going back to our water analogy, resistance is like pinching the hose. It makes it harder for the water or the current to flow. And by the way, this friction is what generates heat in things like your toaster. So there we have it, our three pillars. We've got voltage, which is the push. We've got current, which is the flow. And we have resistance, which is the opposition. Now, these three things aren't separate. They are all locked together in this beautiful, really simple, and incredibly powerful relationship. And that relationship is called Ohm's law. It's so simple. Voltage equals current times resistance. V equals I times R. This one tiny equation is the key to understanding how almost every basic circuit works. This really brings it all home, doesn't it? Voltage is the water pressure. Current is the rate of water flow. And resistance is how narrow the pipe is. Seriously, if you can just remember that water analogy, you've totally got the fundamentals of electricity down. And why does any of this matter? Because this interplay, the push of the voltage and the flow of the current against resistance, is what lets electricity actually do useful work for us. That's what we call power. It's what lights up a bulb, or turns a motor, or runs your computer. And just like that, you now have the three basic building blocks to understand any simple DC or direct current circuit. But everything we just talked about assumes the current is flowing in one steady direction. What happens when that flow starts to switch back and forth dozens of times a second? And how does that bring the incredible force of magnetism into the whole picture? Well, that is a story for another time.
Like and share this video. And don't forget to subscribe to Powered by Tesla.